Well, good morning. Let's see if we can get the slides up. I also have breaking news. It's not quite as dramatic as the breaking news that we had yesterday from Klaus, which told us how we were going to completely redo the units. What I'm going to talk about is something a little less important. This is the origins of life. About 4 weeks ago, the scientists at the Templeton Foundation workshop. The Templeton Foundation has put $5.4 million into a 3-year program to try to break some ice in the origins of life area. We had people from the Tokyo Institute of Technology, from the Simons Foundation, from the Georgia Tech Center for Chemical Biology, as well as our own program. And we decided that life most likely emerged 4.36 plus or minus 0.04 billion years ago based on mineral bisulfite carbohydrate reservoirs, reduced nitrogen organics from a late veneer impact, and phosphoborate minerals. Now, those of you who are in the room, I'm looking around, are much too polite to do what you're supposed to do right now, is to interrupt me and say, how the hell could you possibly know that, right? Because this is actually not a physical law. It's not a statement that can be tested by hypothesis or experiment. It is a statement actually in natural history. And of course, the problem with natural history is that a lot of it's just storytelling, and if you're telling your story, anybody's story can be as good as anybody else's story. And sort of the answer to this, of course, this is not something, therefore, it's approached by standard scientific methods. The Templeton program actually did something which we borrowed from physics. There's this wonderful line from Niels Bohr, which is how wonderful that we have met with a paradox. Now we have some hope of making progress. What we do is pick out paradoxes, which are statements that seem to be indisputable in chemistry or physics or biology. And those statements, if you follow them to their logical Aristotelian conclusion, drive you to the conclusion that life could not possibly have arisen without divine intervention. And if you want to see a list of these, you go to any good creationist webpage and you'll see people explaining how complicated life is and how it could not have been emerging with out of guiding hand. But when you do focus on paradox, the research is much less diffuse. It does not necessarily focus on cultural issues arising in historical questions, whether or not they remain relevant to the major science, but they actually get you into the place where you can make some progress. The other part, of course, is now Richard Feynman, again, a little bit older. You have to really have some intellectual discipline here because people are easy to fool, and the easiest person to fool is yourself. The field has few constraints. People love their own ideas, and few scientists really credit data that contradict their ideas more than data that affirm their ideas, which is what scientists are supposed to do. And so you really have to worry not only that I'm fooling myself, but telling you that story, but also that I'm trying to fool you. So let's have a closer look at some facts. So there's the standard model for life on Earth. You heard this from Otto Jonath yesterday. There is the notion that Darwinism began with RNA catalyzing template-directed synthesis of RNA with replicable errors. That's the core of Darwinism. It's the idea of how you get natural selection to bring order and the properties that we value in biology to chemistry. Alex Rich, actually in 1962, was the first to suggest that, and there's actually an example. This is from Phil Holger's lab. Phil was a former student of mine, and he's now in Cambridge, and there's actually an RNA molecule which catalyzes the template-directed synthesis of RNA made in the laboratory. So that's, if you will, an existence proof. We think we can get these things. What Otto showed you yesterday was the structure of RNA, the ribosome. The RNA is the catalyst that makes proteins. This RNA first model explains, among other things, the fact that the orange parts of the ribosome, the RNA parts, are actually making proteins. That means that proteins come first. This does solve the so-called chicken or egg problem, which is, you need DNA to make proteins and proteins to make DNA, and it also explains why these cofactors are common throughout universal metabolism, including yours, but universally on Earth, including a vitamin you may have had this morning containing niacin, and another vitamin you may have had riboflavin. These are both RNA cofactors that have survived for 4 billion years in your metabolism to do oxidation reduction reactions in particular. Well, that's fine. That's the standard model, but there are 3 parts of RNA. There's the carbohydrate, which we will code as magenta through here. Those are sort of the ribose, the R in RNA, and then there's the nucleobases, or the bases, which are the things that encode the information. You have 4 of them, G, A, C, and U in your RNA. U is replaced by T or thymidine in your DNA. And then there's the phosphates, which are the green negatively charged linker groups. And so prebiotic carbohydrate synthesis is our first paradox, and it's actually one that you're all familiar with if you've ever been into your kitchen and put energy into carbohydrates. So there are some magenta carbohydrates. There's ribose on the right. There's glyceraldehyde, which has 3 carbons, glycolaldehyde, a 2-carbon carbohydrate. And up in the upper right-hand panel, we have an example of what happens when you put sugar in the presence of heat is you get tar, you get caramel, and the more you heat it, you never get something crawling out of the mixture doing Darwinism, right? What you get is something increasingly more appropriate for paving roads than actually doing biology. And the reason for that is this so-called C double bond O, which I've highlighted in magenta in these structures. This is the reactive group that causes caramelization. It's also a very useful group. It's how you actually metabolize glucose, which also has a C double bond O group. But you have Stanley Miller, who's the handsome chap sitting there on the right-hand side behind his generator where he sparked methane and got amino acids out. Writing now 20-some years ago that stability considerations preclude ribose and other carbohydrates. He went after them all as prebiotic reagents. That is, you could not make these compounds because they were too unstable on a prebiotic earth without the guiding hand of God. We'll leave that aside for the time being. And so ribose, he concluded, and other sugars were not components of the first genetic material. Well, this does a serious number on your RNA first model for the origin of life. If there's no ribose, there's no R. If there's no R, there's no RNA, and so that's a problem. But you got to keep in mind there's a bit of rhetoric here, right? Just that's what Stanley Miller in his press release looks like on the left. That's actually what the experiment is on the right, and you can see asphalt being formed in that pot. Many people still quote this experiment as being an example of how you can get biological compounds out of non-biological compounds. Fair enough, but you get biological compounds out of non-biological compounds with a very large amount of tar and asphalt associated with them, and this is a big problem. So there you go. So the carbohydrate C double bond O is invoked in many, many paths to nucleotides. That structure in the lower right-hand corner is actually, for those of you who are not familiar with cytidine, it's one of your 4 bases, nucleotides in your RNA. And there's a whole bunch of structures going. This is actually a model from Matt Pauner et al. In 2009. And so I would give you now a little examination. Can you find the unstable compounds in that mixture? And I mean, we're going to make you all start thinking like organic chemists before the afternoon. But yeah, the answer is yes, every place you have a C double bond O, you've got an unstable compound. But if you must have C double bond O compounds to make RNA, but you may not have them, the conclusion that you can't have this model. And that's, of course, annoying to us all. Well, now, one of the ways to resolve those paradoxes, it's always the way to resolve the paradoxes, is by examining the premises, okay? So when you have volcanic lightning, that's actually what's making carbohydrates. But you know, and that's what's going on early Earth, a lot of volcanoes on early Earth. But they're also producing sulfur dioxide. And of course, what's amusing is that sulfur dioxide cannot help but react with carbonyl C double bond O groups. And that actually forms a very stable sulfonate derivative. Now that reaction is reversible. It's maybe 1 part per million to the left, but the rest of it is to the right. But it becomes a stable reservoir of carbohydrates. And we call this bespoke chemistry because it is as if it were tailor-made. If the sulfur dioxide from the volcano reacts with these carbohydrates and makes these compounds in the lower right-hand corner, the so-called hydroxymethyl sulfonate is this reservoir here for a 1-carbon carbohydrate, but this works for all the others. And the result is that you have a reservoir of these carbohydrates that's stable over a long period of time. So Matt's happy, I'm happy, everybody's happy. But wait, right? A disciplined scientist cannot stay happy, right? We have to worry about these things. So, for example, how do we know that the volcanoes in the Hadean were actually emitting sulfur dioxide? Well, the answer is we can actually go back and find rocks from this. That's actually not an Australian zircon, that's actually a gem quality zircon, but there are zircons from Australia which date to 4.4 billion years. They're nice little stable packages that you can date. There are actually 2 uranium-lead date series that you can follow, so you know if those dates are concordant, that the zircon has not been disturbed. You can look at cerium-3, cerium-4 inclusions in those zircons, which tell you the redox state of the mantle from which those zircon crystals crystallize. And we know from that that there is, in fact, sulfur dioxide coming out of that volcano because that's the redox state of sulfur that is compatible with the redox state in the zircon crystals. So now all of a sudden we have all these structures that are magenta because they're carbohydrates, but I put the yellow sulfur SO3 attached to them, and these compounds are perfectly stable. And in fact, when you get to ribose, you actually have another way of stabilizing it, and that's by making a borate complex. And that's what the green boron is showing, coordinating to ribose in a cyclic structure. And so you have these reservoirs, and the model actually is sort of like the modern surface of Titan, right? In Titan, there's organics being generated all the time. They are frozen out on the surface. There is no biology to eat them, which is why you don't have organics the same way on Earth, but they accumulate and they become a reservoir. Very useful. Well, the zircons also have another clue here. There's also a paradox, right? The question is whether the Earth has any dry land on which to accumulate these reservoirs. There are some people who think that the Earth was a water world, in which case any of these reservoirs would be hopelessly diluted into a global ocean. But it turns out that the zircons help here. I don't have time to go through the argument, but they have clay inclusions actually that look like they're coming from some dry land erosion, and there's an oxygen isotope experiment. And so the plate tectonics gets started late. About 1 Australia landmass is roughly occurring at the time that we're talking about. But what you can now start doing is start putting these plots up. And so you're looking at time on the x-axis, billions of years. And what you're seeing here is these curves where the dry land is going up, the reservoir, of course, is accumulating, and of course, the more dry land you have, the more the reservoir is accumulating, and things get better as long as you go forward in time. But there's now another paradox, right? If the atmosphere had the oxidation state of sulfur dioxide, then it could not have formed hydrogen cyanide. So for those of you who are not in the business, you say, who cares about hydrogen cyanide? Well, the answer is that you should, because as we cut apart this RNA, you'll notice that the bases have these structures which don't have so much oxygen in them. They're actually formed from hydrogen cyanide. And here's, in fact, one of your bases. This is adenine in the lower right-hand corner. You can see these are not oxidized species. And for those of you who are not chemists, the way you notice that is by there's no oxygen in any of them. Right? There's carbon, hydrogen, and nitrogen. In fact, in adenine, there's 5 carbons, 5 hydrogens, and 5 nitrogens. And they're being formed by a synthesis that Leslie Orgel and John Oro pointed out to about 50 years ago. And so now there's this quote from the prebiotic community that everybody agrees that you can have hydrogen cyanide. Everybody puts it into their models, but just because the culture agrees that early Earth had hydrogen cyanide, or this other 2 molecules which I've drawn here, HCCCN, which is called cyanoacetylene, and HNCNH, these are not oxidized, right? No oxygen. Doesn't mean it was there. And the problem is if the atmosphere is in redox equilibrium with sulfur dioxide, which we need to solve the carbohydrate paradox, the productivity of these key molecules is 0, all right? So you get the carbohydrates that you want, the zircons support your natural history model, but you get none of the bases. And people have known about this for 20 years, but prebiotic chemists, my community included, still build models dominated by hydrogen cyanide and all the products that we make from them. It's shameful. In fact, can you now find all the reduced species in this? And again, all you have to do is look for the species that don't have oxygen in them. The slide's a little small for those of you from the back of the room. But there's the paradox. That is, if you must have reduced CN compounds to make RNA, but you cannot have them because the atmosphere is too oxidizing. Carbon is carbon dioxide, not methane. Nitrogen is dinitrogen, not ammonia. Then you can't have RNA, which means you can't have RNA emerging first without the guiding hand of God. I keep coming back to that. But So all the carbohydrate reservoirs in the world are worthless if you can't get the bases. And so now we have to go to another paradox, actually, which comes from geology. And it's based on this notion that when the Earth is forming and still molten, the iron sank to the core, taking with it all iron-loving elements, like palladium and iridium and platinum and gold. And yet you can mine palladium, iridium, platinum, and gold from the Earth's crust today. So where does it come from? Well, the answer that the geologist tells you is that these siderophiles were delivered to the Earth's crust as a late veneer by impactors large enough to have their own iron cores, large enough to reset the radio clocks in the crust, but not large enough to remelt the Earth. And I can't go through all the data, but it comes from the composition of the late veneer on Earth, also from the distribution of the veneer on Earth and the Moon. But the point here is that now you are asking, what happens when a body about the size of the Moon with its own iron core hits the Earth? Well, it resets the uranium clocks in the crust, that's clear. So we know that that impact occurred about 4.47 billion years ago. Now, it destroys any life in the crust and any reservoirs that you build in the crust. You've got to start over at that point. But it dumps tons of molten iron into the atmosphere. And what does molten iron do to carbon dioxide, dinitrogen, and water? Well, the answer is it reduces them to methane, to ammonia, and of course the water is reduced to hydrogen. We probably had about 160 bars of dihydrogen above the Earth, where we have an oxidized sulfur dioxide generating mantle and a reduced atmosphere that's able now to generate these CN-reduced compounds like hydrogen cyanide and cyanamide and cyanoacetylene. So the same impact that delivered the iridium, platinum, gold, and that we mine today from the late veneer produced a reduced atmosphere over the oxidized metal and allowed the bases to rain out onto that surface, which also had the carbohydrate reservoirs made with the volcanic. And so that's the repeat of that slide. So now what we can say is that we don't just have the increasing dry land and carbohydrate reservoirs, but all of a sudden, I'm sorry, I'm doing this. I did not learn my lesson from yesterday. We also now have a time where we can also all of a sudden boost the amount of these organics that are reduced in the atmosphere and make them now a source of hydrogen cyanide, cyanoacetylene, these other compounds that are needed for the bases. Well, actually, not quite, because what happens is that dihydrogen, when it's 160 bars, will gravitationally escape from the atmosphere. And so, in fact, that reducing potential in the atmosphere is transient. It goes away after 150, 200 million years, and that's a model-dependent curve, which I have drawn in cartoon form here. And what that means is that you have a probability of making RNA, which has a maximum of about 3.6, it's actually 4.6 billion years ago. I have to change that. So earlier than 4.6 billion years, ignore that 3 there are fewer reservoirs on less dry land, and afterwards, the hydrogen has distilled away from the atmosphere, so there's less forming of bases. And so what one can now say, that's better, 4.6 billion years. By the way, after 4.6 billion years, if you go down to 4.1 billion years, you actually now have the first isotopic signals of biology, carbon-12, carbon-14 ratios at 4.1 billion years say that about 250 million years after the maximum probability of forming RNA, you actually have widespread biosphere on the early Earth. So, of course, the carbohydrates and the bases are not enough. What about the phosphate? There is actually an amusing point of this reaction where that arrow is saying that this particular combination of a base and ribose cannot occur. It was not impossible. Who said it was not impossible? Well, the answer is Leslie Orgel, who I've already mentioned. It's actually kind of amusing. He said this 50 years ago, and it's great when you're training science students to follow back in time the thread of citation, right? Because somebody cites somebody who cites somebody and cites somebody. And if you have to go back a half a century to get the original reference, it just might need to be revisiting. And of course, it can be revisited because just as from the Earth we have this bespoke chemistry of hydrogen as water, and we also have phosphate in the crust, we have boron at borate as carbon as carbonate, sulfur as sulfur dioxide, as I've already mentioned. And we have the reduced compounds bespoke from the atmosphere. We also have now the ability of just combining these two. This is actually an experiment that was done now 20 years ago by Ram Krishnamurthy, where actually phosphate from the oxidized surface can combine with the bases from the reduced atmosphere to produce cytidine, actually phosphate. It's actually kind of amusing because there are other minerals that combine borate and phosphate, which allow you to make borophosphates. There's something called Lüneburgite, which is on this slide, which not only makes the phosphates of the nucleosides, but actually makes the diphosphates. And if you have nucleoside diphosphates in quantity on the early Earth, in a dry environment, on dry land, you have RNA. So that's basically the story, what you have seen. If you systematically work through all the paradoxes, what you'll come up with is that a late moon-sized impact can account for the late veneer. That's the independent evidence for that impact. But it also solves the need for a crust, an oxidized crust, to allow ribose to survive to exist at the same time as a reducing atmosphere, with bespoke reactions which increase the reservoirs matched by a loss of H2O, giving the optimum probability of RNA forming about 4.36 billion years ago on dry land, where borophosphate minerals gave nucleoside diphosphates and RNA. And these are the people who participated in the conversation. So if you want to know how RNA is formed on prebiotic Earth according to this model, there you are. Let me put that structure here. By the way, I don't know if any of you have ever worked with the Templeton Foundation, but they are always asking you to give you, Templeton was a financier, he always wants you to give a cost-effectiveness statement about what you did. And so here for $5.4 million, we've gotten rid of all of the paradoxes between the origin of Earth and the origin of RNA. Now, I don't want any of you going back and telling your colleagues that this problem is solved, because there are several normal science puzzles that remain on the far side of RNA, and there's some very significant paradoxes that remain on this side of RNA. So, however, I must conclude by offering you an apology, as I offer nothing to solve the civilization-ending, death-creating, ignorant populace problems that were posed yesterday. I do want to say that we do basic research at FAME that has practical value. So we do synthetic biology, which creates extra letters in the genetic alphabet, which is useful for diagnostics and therapy. We have resurrected ancient genes and proteins from the modern biology. We also go look for aliens. I'm sure something practical would come if we found aliens. But Martin wanted me to talk about the one thing that has no practical applications whatsoever. So for that, I apologize. But thank you for your attention.